Unit 5, pages 172 to 175, solving optimization problems. So last unit, we talked a lot about related rates. This unit, we're ending with this idea of optimization, which is determining a maximum or a minimum value given a word problem. So there are about 5 general approaches to solving an optimization problem. First step is determine the quantity that has to be optimized. By optimized, we mean maximized, or minimized. Second step is sketch the picture. Never go wrong with sketching a picture. So sketch a picture. Or write the statements identifying variables or quantities that are not valid or valued. Right, so basically sketch a picture identifying the variables, right? So not just the constant values, but the variables as well. So steps 3 and 4 are kind of the biggest of the 5 steps, right? So step 3, we want to write the primary equation. That represents the quantity that is to be optimized. Right, so if I'm trying to optimize volume, I need to write the equation for volume of that shape. If I'm trying to optimize area, I need to write the equation for area of that shape. If I'm trying to optimize distance, I need the equation for distance, so on and so forth. Step 4, if the primary equation contains more than one variable, a secondary equation may have to be written. To show the relationship between the two variables. Okay, so your goal is to get that primary equation written in terms of one variable. Okay, and then step 5, this is where the calculus comes in. We're going to take the derivative and verify using a sign chart or a sign analysis. That the primary equation is maximized or minimized. Okay, so the next few pages are all example problems. There are 5 examples in total. I'm only going to complete in full 3 of those 5 examples. I'm going to complete example 1, example 3, and example 5. So example 1, a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? And what is the maximum volume? So first thing I want to do is state what it is that I'm trying to optimize. So my goal is to get volume to be maximized. That's my goal. Okay, so this manufacturer is building a box, open box, right? So there's no cover on this box. It has a square base, so that means this side and this side are the same. And the height's probably different. Right, so then since I want to maximize volume, I need the equation for volume, which is, in this case, V equals base times height times width, right? So x times y. So we have x squared y based on what I have. I also know that I have a surface area of 108 square inches. So surface area is equal to 108 inches squared. And the equation for surface area is, in my case, I'm looking for all the sides, the area of all the sides added up, right? So down at the bottom, I have x squared. And then I have 1, 2, 3, 4 sides along the side who have an area of x times y. So I have 4 x times y sides. And then I don't have a top. I don't have a lid to this box. So I can rewrite this as 108 equals x squared plus 4xy. Okay, so I want my primary equation to be written in terms of one variable, right? So we're so used to solving for y in algebra and in other parts of our lives, so let's solve for y with our second equation. So we're going to take the second equation and solve it for y. So I have 108 minus x squared equals 4xy. So I have y equals 108 minus x squared over 4x. So now I can rewrite my volume equation in terms of just one variable. So volume is equal to x squared times 108 minus x squared over 4x. And when I simplify this, I get 108 x squared minus x to the fourth all over 4x, which is equal to 27x minus 1/4 x cubed. So I have completed steps 1 through 4. Now to move on to step 5, where I actually do the calculus. So I'm going to find the derivative of volume. So I want v prime, and that'll be equal to 27 minus 3/4 x squared. So to do a sign analysis, I need to first figure out the critical numbers. So I'm going to set the derivative equal to 0 and solve for my x value. So negative 27 equals negative 3/4 x squared. Divide both sides by negative 3/4. I get x squared equals 36. Take the square root of that. X is equal to negative 6. X is equal to 6. Since I'm looking at dimensions of a box, x can never be negative. So x will never be negative 6. Therefore, x is equal to 6. And when I do my sign analysis, starting at 0, going on for forever, and my critical number being 6, if I check a value between 0 and 6 into my derivative, I'll get a positive number. If I check a value between 6 and infinity, I'll get a negative number. So since v prime changes from positive to negative at x equals 6, volume is maximized. Okay, so I have completed the steps 1 through 5. But now I need to actually answer the questions that the problem is asking me. What are the dimensions of a box with the maximum volume? So I know that x equals 6, right? I also know that 108 is equal to, actually, I also know that y is equal to 108 minus x squared over 4x. So y is going to be equal to 108 minus 6 squared all over 4 times 6, which is going to be equal to 3. So the dimensions of this box are 6 inches by 6 inches by 3 inches, right? Because my box is x by y. And the volume will be equal to 6 squared times 3. So volume will equal 108 inches cubed. Okay, so optimization problems can be a little long. It's all about the way you set up your problem. If you are unable to set up your problem accurately, you will lead yourself down the wrong path, which will lead you to the wrong answer. So it's all about the setup, and that's where most of the time gets put in. So for example number 2, we're not actually going to do example number 2. However, I will help you set this up. So a box is to be built from a rectangular piece of cardboard that is 25 centimeters wide and 40 centimeters long by cutting out a square from each corner and then bending up the sides. Find the size of the corner square which will produce a container that will hold the most amount of soup. So we have a sheet of paper or a sheet of cardboard, and we're cutting out the corners. right? Cutting out the same shape, the same size corner for all four corners. So let's label that XX. All right, so we're cutting out all these X by X squares. And we want to create this type of rectangular box back there. We know that this cardboard is 40 centimeters long and 25 centimeters wide. Right, so what that means is when we create this box, after we've cut out these corners, our width is going to be 25 centimeters minus the two sides that we cut out here, so minus 2x, and our length is going to be 40 centimeters minus the two sides that we cut out here, so 2x. And then our height is just going to be the height of what we cut, so this height is going to be x. All right, so our goal is to maximize volume, right? So this is everything we need to know to solve this problem. Now it's a matter of figuring out how do I apply what I know about volume in this box to help me solve this problem. So try example number 2 on your own. Example number 3. Rectangular page is to contain 24 square inches of print. The margins at the top and the bottom of the page are to be 1.5 inches, and the margins on the left and the right are to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used? So this problem is asking us to maximize or minimize area. Right, because we want to use the least amount of paper, so we're minimizing area. So let's sketch what this problem is looking like. So we have text that takes up 24 inches squared. And that text is going to be on a sheet of paper where the margin on the left and the right is 1 inch. And the margin on the top and the bottom is 1.5 inches. We want to know the dimensions of the entire page. So if I label this inside page where the text is, if I label that just XY, then the entire page, the length of the entire page will be X plus 1/2 plus 1.5. So we have X plus 3. And the width of the page will be Y plus 1 plus 1. So Y plus 2. So we know that the area of the whole page will be equal to Y plus 2 times X plus 3, right? Length times width. We also know that the area of the text is equal to 24 inches squared. And to find the area of the text, we just do X times Y. So since I have two equations, I want my primary equation to be written in terms of one variable. So I'm going to solve my secondary equation so that it's solved for y. So y is going to be equal to 24 over x. So now I can rewrite my primary equation as a equals 24 over x plus 2 times x plus 3. And I can simplify this by multiplying it out. So we get 24 plus 72 over x plus 2x plus 6. And I can rewrite this in polynomial form as a equals 30 plus 72x to the negative 1 plus 2x. So I've officially completed steps 1 through 4. My primary equation is in terms of one variable. So now, step 5, I'm going to find the derivative of that equation. So I get negative 72 x to the negative 2 plus 2, which can be rewritten as negative 72 over x squared plus 2. Okay, and then to use sign analysis, I need to set this equal to 0. So 0 equals negative 72 over x squared plus 2. So 2 equals negative 72 over x squared, which gives us 2x squared equals negative 72. That should be negative 2. So then x squared is equal to 36, x equals negative 6, and x equals 6. And since, again, dimensions, can't have negative dimensions, so my x is equal to 6. All right, so to do sign analysis, smallest dimension I can have is 0, and then my critical number is 6, and we're looking at the equation a prime. So between 0 and 6, if I plug in a value into my derivative, I'll get a negative number. And from 6 on, if I plug in a value into my derivative, I'll get a positive number. So since a prime changes from negative to positive at x equals 6, area is minimized. Okay, so now I need to actually answer the question, right? So what should the dimensions of the page be so that the least amount of paper is used? So we know that the page is y plus 2 and x plus 3, right? These are the dimensions. This would be the width, and this would be the length. So we can find the length pretty easily. We know what x is. X is 6. So 6 plus 3 equals 9. So 9 inches is the length of our sheet. But now we need to know the width. So we need to know what y is first. So we know that y equals 24 over x, which would be 24 over 6, which equals 4. So since y equals 4, we can plug that in here. So we have 4 plus 2, which is equal to 6. So our dimensions are width is 6 inches and length is 9 inches. So now, for example 4, again, this is a problem where I'm not going to work through every step with you. However, I will help you to set it up so that you start off on the right path. A rectangle is bound by the x and y axes in the graph y equals 3 minus 1/2 x. What length and width should the rectangle have so that its area is maximized? So here we are maximizing area. Okay, so we know the rectangle is bound by the x and y axis. So we'll just label the sides of the rectangle x and y. And there's going to be some point on this graph where we have maximized the area of this rectangle. So we know area of a rectangle is equal to length times width, so x times y. This is one of those problems where we don't have to create a second equation because we already have one, right? So all we need to do is use the y equals equation in my a equals xy in some form to move forward and find our answer. So I want you to try example number 4 on your own. Example number 5 is a bit trickier. You want to determine the point on the line y equals 2x plus 3 so that the distance between the line and the point 1, 2 is a minimum. So here we're trying to minimize distance. Okay, so we want some point xy where the distance between that point and 1, 2 is minimized. So for minimizing distance, then my first equation has to be about distance. And if you remember from pre-calculus or from geometry, distance equation is square root of x1 minus x2 squared plus y1 minus y2 squared. So our first point is x and y, and our second point is 1 and 2. So we can rewrite this distance equation as x minus 1 squared plus y minus 2 squared, square root of all of that. So this problem is similar to the one above where we don't have to write a second equation because we're given a second equation. We know that y equals 2x plus 3. So we can rewrite the distance equation as square root of x minus 1 squared plus, and since y is 2x plus 3, minus 2 squared. And we can simplify this, get the square root of x minus 1 squared plus 2x plus 1 squared. So the next step here is to try to simplify this as much as possible before finding the derivative. So if we actually square these two things, we get square root of x squared minus 2x plus 1 plus 4x squared plus 4x plus 1. And then combine our lovely like terms, we get the square root of 5x squared plus 2x plus 2, which we can rewrite as 5x squared plus 2x plus 2 to the 1/2 power. So now I have officially completed steps 1 through 4. And my next item of business is to find the derivative. So the derivative of the distance equation, we're going to have to use chain rule here, is 1/2 5x squared plus 2x plus 2 to the negative 1/2 times 10x plus 2, which is equal to 10x plus 2 over 2 square root of 5x squared plus 2x plus 2, which I can further simplify to 5x plus 1 over square root of 5x squared plus 2x plus 2. Okay, so our job is to get the derivative equal to 0. That happens when the numerator is equal to 0. So we want 5x plus 1 to equal 0. So 5x is equal to negative 1, and x is equal to negative 1/5. So since this graph goes both positive and negative, our sign analysis only has one critical number, and that's at negative 1/5. So any number less than that, when we plug in, actually gives us a negative value, and any number greater than that gives us a positive value. If you don't believe me, you can check. So since d prime changes from negative to positive at x equals negative 1/5, distance, sorry about that, I'm not entirely sure what happened there. Distance is minimized. So now we have to actually answer the question. We want to determine the point on the line. So we know that x is equal to negative 1/5. We also know that y is equal to 2x plus 3. So if we substitute in for x, we get y is equal to 2 times negative 1/5 plus 3. So y equals 13/5. So our point is negative 1/5, comma, 13/5. So that's the end of this video. Optimization is not exactly on the test for this unit. However, it will be tested in the future and you will have an extra credit opportunity to complete for this topic.